Hi guys, so today we will start with a new question from group B, which is question number 11, which states that we have to write a Python program to store roll numbers of a student in an array who attended a training program random order. So we have to write a function for searching whether particular student attended the training program or not. So we have to use either linear search or sentinel search. So let's just see how we can do this. Let's just first of all copy this question and move on to our text editor. So let's just paste this thing. Let's just paste this thing and save this file. So let's just comment this out and think of it. So first of all, they have said we need an student array which would contains the roll number of in random order, and then we have to implement the searches. So let's just see what are the basic searching thing, or what is a basic search. So let's just assume that we have a list and which would have some random numbers. Let's just say 23, 25, 19, 8, 9, 15, 35, 97, 86, 67, 45, 53, 99, 90, 87, 77, 68, 59, etc. So these are the numbers which we have. So what we have to do is, let's just say I want to search for roll number 18. So what would I do? I would have to search from this list. So these numbers. So we can basically see few numbers at a glance, and by checking we can see 18 is not present. But if this list is more bigger and it has 100 to 200 elements, so how would we see? Basically, the first of all thing we would do is we would either start from beginning or the end, and we would start checking each element. So is this 18? No. Is this 18? No. 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 So like this we will go on checking, and if we found it we will return it, but here we can't found. So basically we are not getting this element. Similarly, let's just check for any another element. So now I want to search for roll number 97. So how would I get it? So again I would search for 23, no, 25, no, 19, no, 8, no, 9, no, 15, no, 35, no. And then we check with the 97 and we got our key. So basically like this we can find. So here we can see we are going one after another in a line. So here we are searching in a linear fashion. So this searching is called as linear search. So basically if we have a list, we know how we can iterate through the list. So basically, if we know how we can iterate, we have to just check whether that current element is the element we require or not. So if it is the element, then we return it. So basically, instead of returning the value, so here as we can see, we have to find for 97. So what would we do is, instead of returning 97, we would return the index or the address where this exists. So we have to basically return that, because key is already present. We either need the position of that array, means position of that element, or anything else. So let's just go back to our editor and let's just see how we can do this. So first of all, we would need a students array in which we would store all the roll numbers. So let's just create one. So I will create a student list and I will put the elements. So 10, 40, 45, 67, 89, 34, 56, 78, 73, 90, 1, and 37. So these are the values I would take. So as we can see, these are in random order. They are not sorted. So basically we will see what is sorting. But for now, these are in the random order. Any elements can come anywhere. So what we have to do is basically iterate. So first of all, we would also need a key to check whether that means basically we should know what is our target, for which element are we searching. So basically, instead of declaring these separate things, let's just create a function. So function linear search, and we will take some arguments such as list, and then we would need a key or target, anything you can call. Basically, then what we have to do is we have to iterate through the whole list. So I will iterate through the list. So for num in student list, instead of num it should be roll number. Let's just modify this for roll number, roll num in student list. What we will do is if roll num equal to, so the key provided by the user. So if this is the key, we have to return the index. So basically we have to return that index. So instead of directly looping, what we will do is we can use range function. So let's just use range, then length of student, and instead of roll number, now we should take I, and here instead of checking with the index, we have to check for that element. So stud list of ith element. So like this we have to check. If we found it, we will return I, else what we will do is we will return -1. So basically we will return that we -1 would say that currently that element is not found. So let's just try printing this. So print linear search. So linear search, then list would be the student list, and the key would be, let's just say 56, and let's just execute this. So here I can see 6. So let's just format this a bit. So student is present at 6th index. So present at position, let's just put position and 6. So let's just also put this linear search. So linear search, and yeah, this should be all. So let's just again execute this, and linear search student is present at 6th position. Like this we can get, or what we can do is we'll put this at last, so it would look better. So yeah, student is present at 6th position. Similarly, let's just change this to key, which would be, let's just say 1. So here we are getting 10th position. So let's just check whether this is correct or not. So let's just give 40, which should return us index 1. So yeah, here I can see it is returning me index 1. Similarly, let's just put anything which is not present. So let's just put 500 and execute. So here we can see student is basically, if let's just put a if condition, if this linear search, so let's just store this value somewhere so that we can easily access. So yeah, index equal to this thing, and if index equal to -1, means we can say student is not present. So let's just copy this and put it in else, or we can do something here also. We can directly put a ternary operation, but for now let's just keep it. So student is not present, not present, and we will use the linear search as it is, and if he is present we will print the index. So this should work fine. So student is not present, here we can see. So let's just try to compute the time complexity. So here, as we know, for loop takes order of n time and we don't do anything else. So this linear search has order of n. So if you are still figuring out how order of 10, let's just see this. So here we are back with the same question. So what we will do is we will basically check how order of n comes. So let's just forget everything about time complexity and we will start from a very general case. So here let's just say I have to search for any element. So what is the maximum or minimum number of time I would require, instead of time, let's just say how many steps we would require. So here, if we are finding for 97, it is approximately one first step, second step, third step, fourth step, fifth step, sixth, seventh, and we are finding it eighth step. Basically, like this, we are finding it at eighth step. So similarly, this can be any random value. But what is the minimum value and the maximum value? So here, let's just say in some hypothetical condition, we are checking for 23. So if we are checking for 23, then we are getting it in first check itself. So basically, can we find out in zeroth check? No, we have to at least do one check to see whether that element is the required one or not. So basically, once is the minimum number of steps we require to check. Similarly, if we consider about the maximum case, what would be it? So it would be the first condition which we saw. The number doesn't exist. So we check for 23, we check for 25, 19, 8, 7, 9, 15, 35, 97, 86, 67, and like this we go on checking everything, but we still don't find. So how many check we did? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 16, 17, 18. So we did 18 steps at max. So can you see this? The number of elements and the number of checks we did. So it is same. So basically, if I assume my list contains n number of elements, then what I can say, my search complexity maximum. So we use maximum using order of n. So it's not that specific, but for a general idea, we can say order of n. So order at is the worst case kind of. So not the worst case time complexity, but it is an upper bound for any of the algorithm. So every case would be below this thing. So it would be below order of n or any linear function. So here also we can see we have only n. So we can call this as linear function. So like this, we basically see this is very generalized method to find time complexity. For other things, we can calculate the steps of for loop and check everything. But this is the basic way. So like this, we can say that linear search uses order of n time complexity. So big O of n. So there are some notations we will be using big O of n. So for learning more about this time complexity, what you can do is you can check out video, time complexity video in my channel, or for more in-depth tutorial, what you can do is I will recommend you a video by Abdul Bari sir. So they have explained this very beautifully. You can check that out. Or if you like any other mentors teaching, then you can prefer anything. You can just search time complexity on YouTube or anywhere and you can learn that. So this was a thing for the linear search. Now they have asked for Sentinel search. So let's just see why we need this and how it will be useful for us. So let's just go to our previous example and remove these things. So let's assume this is our that same list. So what we would have to do is basically now as we saw we have to linearly go through each element. So here were 18 elements, we required 18 searches. Let's just assume we have 1000 elements. So how many search we would require? 1000 searches. Similarly, if 10,000, then 10,000 searches. So this isn't that good. So if we consider each search as 1 second, so it takes less than that. But for general approximation, if we take 1 second, then this is done within half second. So the first case is done within half a second. So this requires 1000 by 60. So kind of 6 1 are 6 40. So 6. So approximately it requires 16 minutes. So yeah, you can see here we basically required half a minute. So if we consider some approximation half a minute, and here we require 16 minutes. So here was a half a second. Sorry, yeah, uh, no, half a minute because we are considering each thing as an second. So here half minute and here 16 minutes. So this is very big time loop, and we just consider thousands. In an university, we can see there are lakhs of students. So if we have to search for any of the student, then this case isn't that good. So uh, another approach given by some other persons where what we can do is they said that just remove this last element of the list and append some your key. So basically whichever key you are searching, just put that here by removing the last element and check for each of the elements. So basically in this case, don't use the for loop, use while loop. Now you would think, what is the difference? Both of them work same. So we will see this difference a bit later, but for now just try to understand what the Sentinel search says. So just remove the last element, so kind of replace the last element by key, the element which you are searching, and then use a while loop for searching the element. So if you found, then you can directly return that index, or if you didn't found, then just go on searching. So here if we are using while loop, we require a condition that that condition should be false, because if that doesn't happens, then what would be, the while loop will go into infinite loop and it would cause issues. So what we will be doing is, we will be starting from here, we will be checking each elements, and like that we will be going. And if we found somewhere, so let's just say we were finding 77 and we got here, so we can stop here. But what if the element is not present? Then we will go on checking, and here at last we will somehow get that key because we have replaced that. So then what would happen if this 59 we are searching? So this, I just said, we have to replace this last element. So this will be stored somewhere. At last, after doing all of these comparisons, you have to check that with the last element. If you found this, means if the key is the last element, then you can return this. If this is not, then what you can do is, you can just print my -1 or none. You can just return that we didn't found that value. So this was the basic case of how the Sentinel search works. So you would have got an basic idea. But now you would be thinking, why while loop, and why we are removing these all things, and what is the benefit? Both loops work same. So here, let's just deeply analyze the how the for loop works. So let's just take for, and we would be having I in range, and let's just say 10. For now we will take n, and we are here doing one computation that let's just say student list of I equal to key, equal to key, and we are then returning. So this takes 1 unit of time, this return, and external return takes 1 unit of time. So this take 1 units of time. Let me just change this. So here return, and yeah, this takes 1 unit of time. If it executes, this takes 1 unit of time. Between these two, any one would appear. So let's just consider the inner thing. You can consider any of the thing, but let's just for now consider the inner thing. Then what would happen is, basically now, first of all, a range would be created 1 to 10. So at first I will be assigned to 1. So we will assign I equal to 1, then I equal to 2, then I equal to 3. So basically what we are doing, we are doing an assignment operator. So we can consider this thing as a single statement. Okay. So at first we initialized. So that is one single statement. Then we check if this is condition or not. If this is not, if this is the condition or not. So we check here one time. So then what we do is, if this is not the case, we go again, the value is incremented. So kind of, if we generalize this for loop a bit more, so what we can do is, for, we can use the generalized pseudo method. So we first initialize I equal to 0 and I is less than n and I plus plus. So this is the basic thing. So here what we do, this takes 1 unit of time, then a condition is checked every time. So this takes 1 unit, and after performing, this takes 1 unit. Then again the condition is checked. Let's just say this is 10. So what would happen, I would be incremented to 2. So again this would be 2. sorry, so I would be incremented. That time this would be 1, and after incrementation I would be 2. Here we will do a second check, then again I will be incremented to 3. We will do here third check, so then fourth and third. So after this is fourth, this is fifth, so sixth, sorry, and this is fifth, then sixth, then seventh, then eighth, then ninth. So when here we get the 9, 9 is less than 10, yes, then again I plus plus increments and we get 10. So now if we are checking 10 is less than equal to 10 or not, so what would happen, this would return false and we will exit. So here basically this I equal to 0 takes 1 unit of time, plus this takes 10 units. So basically n was 10, so this takes 10 units. So let's just put n, and this does n plus 1 times. As we can see, this checks for n plus 1 times. So we will put here n plus 1. Again the internal body. So let's just say there it has only one statement which is written. Instead of written, what we can say is there is something other statement which takes 1 unit of time. So again plus 1. So if we check this, so this is basically 2n plus 3. Okay. So if we do a bit deeper analysis of this for loop, then we get time complexities, or time complexity is 2n plus 3. Basically this is the value for linear search. So in this we again consider this if case and maybe plus 4. No, we have already considered this single statement which comes under if. So basically this 2n plus 3 is the actual linear search time complexity, but we can go into more depth. We can check assignment operators unit of time, comparison unit of time, means how much time those operations take, and we could then define more clear, more accurate time complexity. But for now 2n plus 3 would be our average case. So this is the value. So yeah, for linear search we saw this is the value. So now let's just search, let's just see how the Sentinel search works. So first of all, what we will do is, let's just say student of last element. So we can use Python negative indexing. So -1 equal to the key. So first of all we have to store this value. So let's just take L, last element equal to SL of -1. So this is stored somewhere. So this takes 1 unit of time, this takes 1 unit of time. Then what we do is while s of I, while s of I we don't get any value. So sorry, while we have to also, basically what we can do is yeah, I is initialized, and here if this is the case, then what we can do is I equal to 0. This is the third statement. So there was a bit uh, difference in this last case, so we'll just say this omit, and then we will again go to that Sentinel search. Just remember the point. So here, as I said, that body will execute only one time, so it execute one time for one loop. So we are here going n times, so this is basically n loops. So what will this do is this would be bit modified 3n, and why plus 3 would remain as it is because this return would happen. If we assume this return would happen, it would take 1 unit of time. So basically 1 plus n plus 1 plus n and 1. So this n plus 1 is separate thing, is it is for the condition. This is for the incrementation, this is for the initialization, this is for the return, and this is for the body execution. So totally 3n plus 3 is the time complexity. Yeah, so just remember this, we will come back to it later. So let's just again go to our Sentinel search. So here we saw this takes 1 unit of time, this takes 1 unit of time, and we put an counter which takes 1 unit of time. Then we check if s of I is not equal to 0. So sorry, if this is not equal to key, not double times. So this, if this is not equal to key, then what we will do is we will just increment I. Okay, so we will just increment I, again check and continue. So whenever s of I means some value becomes I plus plus, not I plus plus, I plus equals 1, as we are working with the Python. So I plus equals 1. As we are working with Python, it should be I plus equals 1. So then what, basically this would be the code, and then we have to check if the I, so after we, okay, so if we get this, then I may be pointing to last element, or I may point to somewhere in between. If it find any key somewhere in between, it may return any middle value. So what we can do is, if I is equal to the last value, which is n minus 1, basically in the array it is n minus 1. So if I is equal to n minus 1, means we are checking if I is the last element. Let's just modify this a bit. So what we can do is, uh, just remove this. So we would check if I is not equal to last element. So if it is not equal to last element, then we will return I. Why? Because that is the number which we, that is the index where we found the number, and it is not the last position. So if it is the last position, then we have put it. So that shouldn't be the case. So if I refers to the last element, means it is not at that place. It may be or may not be, because last element we haven't checked. We have just modified it in the above condition. So we can't say whether this I is the last element or not. But for now, if it is not the last element, then we are of course sure that it is the index where the element is present. So we can return I. Similarly, then what we can do is, then we can check if, else if it is not the last element, then what we can know is, then we know that it is pointing to the last element. So as it is not pointing to last element here, if we check it is not pointing to last element, then we return. If this is not the case, means it is pointing to the last element, so I is pointing to last element, then we can check if the value we stored in L, the last element, is equal to key. If it is equal to key, then we will return I. Or what we can say is, if L is equal to key, then we could return the last element, which is return n minus 1, or it can be also written as I, because I will also point to the last element. So if this both cases are not true, then we didn't found, so we can directly return minus 1, means we didn't found. So let's just reduce this a bit and see this whole method. So now you would be able to see this. So here at first what we did is, we first did an assignment, so this takes 1 unit of time. Then we modified the last element, 1 unit of time. Here we did a calculation, 1 unit. And while, so how many times this would work is at most n times. So maybe this condition would be checked. So here we can see, we will start with 0 up to 10, the same condition which we saw. So at the first 0th case, this will be checked. So 1 will be checked, and if this is not the case, this will happen. If again second time check, so second, then third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So at the 10th position, what we are getting is that element is possible, so it will not go inside this body. So means what would happen, this would go to 2, 3, 4, 5, 6, 7, 8, and 9. So 10 will not be there, so we can say this would be n minus 1. Why? Because if the value is 10, then it will directly exit this, so it will not go inside the loop. So this takes n unit of time, the above condition, and inner condition takes n plus 1, sorry, n minus 1, n minus 1 unit of time. Then this may take 1 unit, this may take 1 unit, and this may take 1 unit, and returns also may be considered. So here we can see 1, 2, 3, 4, 5, 6, 7, 8. So 8, the constant ones, then an n and n minus 1. So if I use this, reduce this, so here we get 2n plus 7. So last time for the linear search, what did we computed? It was 3n plus 3. So between these two values, which is the minimum? So sorry, this may be out of the screen. Just a second. I will just move this a bit. So here now you would be able to see. So let me just recompute this. So what I did was I calculated this once and I got 8. So after getting 8, so what I did here was I computed all the ones. So basically it gave me 8, and after 8 then I computed this n and n minus 1. Basically if I compute 2n minus plus 7. So this is the time complexity I get for Sentinel search. And if you can recall, the linear search time complexity was 3n plus 3. So if you can compare this, so which is greater? Linear search is greater and Sentinel search is more efficient, we can say, or takes less time. So this is less. I just change this color. So this is less and the below one is more. So here we can say linear search takes more time than Sentinel search. So if we consider this using big O notation, both would give me the order of n because we neglect the constants. So both would give an order of n. But whenever we go in depth, a bit in deep, and we check, then we can see the difference. So basically Sentinel search is more efficient than linear search. So this is why we learn the time complexity and thing to see which of the algorithm would be best for us. So now you would have got why we use Sentinel search, why Sentinel search was created, and why we use this more, because it takes less time than linear search. So yeah, let's just go back to our thing and code this thing. So let me just copy this same so that I can use this template and work on it. So let me just paste this, and instead of linear, let me just modify this to Sentinel. Okay, so then what would we do is yeah, instead of for, we have to do that steps. So first of all, the last element would be equal to last of -1. Okay, uh, instead of list, maybe we should give L, because what happens is sometimes this list is internally called means this list is a keyword, so we shouldn't use any keyword here. Instead of student list, this should be list, and let's just modify this to L. Here also it should be L. Yeah, this should work fine. Similarly here also, let's just modify this student list. No, this is correct, so we have to just modify here and it is done. Then the L of -1 would be equal to something, let's say key. Okay, so then after changing the last element, we have to take an counter. So let's just take an I, and while L of I is not equal to the key, so the key, sorry, while, yeah, so while it is not equal to key, what we will do is I plus equals 1, and then at last if, so I may be pointing at the last position or I may be pointing at some another position. So we will check if I is not equal to the last position, which is length of L -1. Yeah, so this should be the value. So if it is not equal, so what we can say is we can directly return, means we found the found this value somewhere in between the list. And if this is not the case, so else what would happen is, or let's just put if, so yeah, or we can also put else. We have to put a condition else if I is no, here we have a guarantee that if this is not true, means it is at the pointing at the last position. So we have to basically check if last equal to the key. So if last is equal to the key, means we found that at the last position. So we could return length of L minus 1. So length of L minus 1, because that's the index and array is starting from 0. If this both are not the case, then we will return we didn't found the value. Yeah, so this would be the basic Sentinel search. And if in more depth, we could write 2n plus 7, and the linear search is 3n plus 3. 3n plus 3, and we would have to remove this Vigo, because Vigo doesn't consider constants. So this is the basic thing. So yeah, instead of this linear, let's just modify this to Sentinel search, and let's just execute. So here both the values are same. This thing is not present. Similarly, let's just modify this a bit to 500. Instead of 500, let's just put 34 and execute. So both are finding the same location, position 5. Let's just again modify this to something like 87. 87 not present. So like this, both of the things work. So here in this session, we basically saw how we can use linear search as well as the Sentinel search to find or search an element in a list. So this would be all for this thing, and let's just meet in our next video.